Dear students, continuing with our next lecture on medicinal chemistry, this is our 19th lecture, and as far as antiviral agents is concerned, this is our 5th lecture. In the first 4 lectures, we have discussed about various types of antiviral agents and various types of viruses which are commonly found in our body. In addition, we have discussed the mechanism, how the virus replication cycle for different types of antiviral agents they can inhibit under different categories of classification. And in the second lecture, what we have done is we have discussed that what are the various types of anti-HIV agents. And in the second lecture, we have particularly discussed the synthesis of HIV protease inhibitors. In third lecture, we have discussed about the synthesis of various types of nucleoside or nucleotide reverse transcript inhibitors. Whereas in the fourth lecture, we have discussed about non-nucleosidic reverse transcript inhibitors. Now in this fifth lecture, we will discuss mainly DNA polymerase inhibitors. DNA polymerase inhibitors, what they will do, they will inhibit the activity of enzyme DNA polymerase. So by inhibiting the activity of DNA polymerase enzyme, what they will do is they will stop the polymerization of the DNA, and therefore a virus will not be able to replicate. The most common among these DNA polymerase inhibitor is acyclovir. This is the IUPAC name of acyclovir. So this is basically a derivative of purine. For the synthesis of acyclovir, what we do is we start with guanine, and guanine, can exist in these two structures, amidic structures and enaminic structure. So when this is reacted with this trimethyl group derivative, that is hexamethyl disilazane, what this will do, this will protect this hydroxyl group and this amino group. So these hydroxyl group and amino group, they will be converted into trimethyl silyl derivatives of this OH, or trimethyl silyl derivative of this amino group. So that means now we are left with this secondary amine group, which can undergo N-alkylation with this molecule, that is 1-benzoyl oxy 2-chloromethoxyethane. So basically what will happen, this will act as a nucleophile and will attack this carbon with the elimination of this halogen. So Cl from here, H from here, this N nitrogen carbon bond will be formed, and we will get this type of N-alkylated product, followed by hydrolysis, and that hydrolysis will regenerate this keto and amino group through hydrolysis of N trimethylsilyl group will be hydrolyzed, and O trimethylsilyl group will be hydrolyzed to regenerate amino group and the keto group. Okay. Then when this N-alkylated product is reacted with ammonia in methanol, basically what happens is that hydrolysis of this benzoyl group will take place and OH will be generated, and this will lead to the formation of acyclovir. This is which is a purine 6-zone derivative. And another method for the synthesis of acyclovir is that if instead of the purine which we have used in the last method, we start with 2,6-dichloropurine. Now you can see that in the previous method here we are having ketone and here we were having amino group, and we needed to protect those groups. And now because of the presence of these halogens, we don't need to protect these groups, and N-alkylation can take place directly with this benzoyl oxide derivative. Again, same reaction, you will get this type of dichloropurine derivative N-alkylated. Then this N-chloro-2,6 dichloropurine derivative will react with ammonia. That means both the halogens, they will be replaced by amino groups. Then when this diamino 2,6 diamino group will be formed with on reaction with ammonia, and when this will react with the NaNO2 in presence of acetic acid, then one of the amino group will be converted into keto group. First amino will form a diazo compound, and on hydrolysis that will be converted into OH group, and then this uh, ketoenol tautomerism, this will be converted into ketonic amide. And then in the third step, this will react with ammonia. Again, the hydrolysis of this group will lead to the formation of acyclovir. So this is how the commonly used DNA polymerase inhibitor acyclovir can be synthesized by these two methods. Then next is ganciclovir. Again, this is the UPSC name of this. This is again a purine 6-zone derivative like acyclovir. So the structure is similar to the previous example which we have seen, but here the starting materials, they are different. We start with epichlorohydrin with benzyl alcohol, and when this is reacted with under basic conditions aqueous sodium hydroxide, basically this oxygen, because of having two lone pair of electrons, will act as a nucleophile, and this will attack over this carbon with the elimination of the halogen, and opening of the uh, ring will also take place due to hydrolysis, and we can have this type of product. If you see this product, this is basically a glycerol derivative. So dibenzyl glycerol will be formed as the product. And when this dibenzyl glycerol is reacted with paraformaldehyde, then paraformaldehyde will react with this OH group with the formation of the corresponding alcohol, which will be converted into a halide of this type. So chloromethyl ether will be formed in presence of dichloromethane in presence of HCl. This chloromethyl ether derivative of uh, dibenzyl glycerol on reaction with potassium acetate in acetone will be converted into this type of 2-acetoxymethyl. This is acetoxymethyl 1,3-dibenzyl glycerol derivative, and then this 2-acetoxymethyl derivative of dibenzyl glycerol will react with N and diacetyl guanine. So this is you have seen guanine in the previous slide. Here it was NH, so one acetyl group. Here it was NH2. This is another acetyl group. So NN dash dies acetyl guanine will react with this acetoxymethyl dibenzyl glycerol. And basically what will happen, this will react after the hydrolysis. At this place we will get the purine glycerol dibenzyl glycerol derivative as the product by reaction at this nitrogen. Then this will undergo reduction in presence of hydrogen and platinum hydroxide on carbon, and this reduction will lead to the hydrolysis of this carbon oxygen bond. So this dibenzyl group will be removed and replaced by hydrogen. So dihydroxide or glycerol will be formed, and purine glycerol derivative will be formed as the intermediate. And then this intermediate on hydrolysis in presence of ammonium hydroxide methanol, this acetyl group will be removed, and this will be primary amino group will be generated back, and this is gan-kiclovir as the product. Again, this is a derivative of purine 6. Then is pan-kiclovir. This is synthesized from the alkylation of 2-amino-6-chloropurine. Again, this is a purine 6-own derivative, but having a different substituents present. So the alkylating agent with which the N-alkylation will take place is this one, 5,2-bromoethyl 2,2-dimethyl 1,3-dioxane, and this is synthesized from this type of tricarboxylate derivative. So when this tricarboxylate derivative is reacted with sodium borohydride, what happens is ester will undergo reduction followed by hydrolysis in under acidic conditions, leading to the formation of this type of butane 1,4 diol as the product. And this butane 1,4 diol derivative on reaction with this type of methoxy ether will, in presence of paratoluene sulfonic acid and triethylamine, will give you cyclized product. So methoxy from here, H from here, methanol will be removed. Here also methoxy from here, H from here, this will be removed, and this isopropyl group will give you a cyclized product. So we will get 1,3-dioxane derivative, and then this hydroxyl group will be converted into bromo group. When this is reacted with carbon tetrabromide in DMF in presence of triphenyl phosphine, the alcohol will be converted into the corresponding bromo derivative, and then this bromo derivative will undergo N-alkylation with this 2-amino-6-chloropurine. So this nitrogen will attack over here, and halogen will be removed. H from here, Br from here, carbon nitrogen bond will be formed. So we will get this type of 9 substituted purine will be formed, and at 9 position we are having this type of 1,3-dioxane derivative as the N-alkylated product. And when this is refluxed under acidic conditions, the hydrolysis of this dioxane will take place in presence of acidic medium, and then in presence of sodium hydroxide we will get this dihydroxide or diol derivative will be regenerated, and this is how panciclovir can be synthesized. Then is Kiclovir. Famkiclovir is again a similar type of compound. This is purine derivative. Basically, only thing is different from others is that here in the previous cases we are having a ketone group, that is purine 6 ones, but this is purely a purine derivative. So when 2-6-chloropurine is reacted with 1,2-dibromoethane in dimethylformamide as the solvent. Basically what happens is this will act as a nucleophile, again attack this carbon with the elimination of bromo group, H from here, Br from here, then N-alkylation will take place. So 1 mole of this, 1 mole of this will give us this type of N substituted, 9 substituted purine derivative will be formed. Then this reacts with diethyl malonate. This 9 substituted purine derivative will react with diethyl malonate in presence of a base. We know this is an active methylene compound. A carbanion will be generated in presence of the base, and that carbanion will attack this carbon with the elimination of Br. So H from here, Br from here, this diethyl malonate will get attached to this carbon. We will get this type of substituted product. Then reduction of this substituted product with sodium borohydride. We know esters, they are reduced to alcohols in presence of sodium borohydride. Then reduction with hydrogen on radium and charcoal will convert this halogen is substituted by hydrogen. And then reaction with acetic anhydride in acetic acid, acetylation of these hydroxyl groups will take place, and we will get famkiclovir as the product. So this is how, in a simple methodology, 2-6-chloropurine can be converted into famkiclovir. Then is valaciclovir. This is basically derived from another antiviral agent, this synthesis of which we have described in the previous slides, acyclovir. So when acyclovir is reacted with substituted alvaline derivative, which is this amino group is protected by carbobenzyl oxy group. When this is reacted, basically this is a carboxylic acid derivative. This will react with this alcohol, and esterification will take place in presence of these reagents, DMAP DCC method, in presence of DMF as the solvent and reagent also. So when both these substrates, they are reacted at room temperature for 2 days, the esterification of these groups, acid and alcohol, they undergo dehydration to give us these types of esters as the product. And then this carbobenzyl oxy group, which is a protecting group, that can be removed if we react this with hydrogen in presence of palladium on alumina in DMF as solvent. Hydrolysis of this or deprotection of this amino group take place, and we will get valaciclovir as the product. Then another method is that this can be synthesized in presence of an enzyme, hydrolase enzyme. So this was a chemical method. This is a biochemical method. So biotransformation of acyclovir with this alvaline methyl ester can also lead to the formation of pure valaciclovir as the product. So here we can say trans-esterification reaction is taking place in presence of this enzyme, that is hydrolase. Here it was a esterification, here it is one of the ester reacting with the alcohol. So methanol will be removed and we will get this type of. Then is valganciclovir. Valganciclovir is again an antiviral compound which is basically alkyl ester product drug of the previous antiviral drug ganciclovir, which we have synthesized in the previous slides. So when ganciclovir is reacted with trimethyl orthoformate in trifluoroacetic acid and DMF, then basically what happens is these groups, they got protected to form a 1,3-dioxane derivative. And in the next step, formic acid then reacts with this and formate of this 1,3-dioxane will be formed. So ganciclovir oxygen monoformate is formed. So this monoformate then condenses with N-benzyloxycarbonyl L-valine. So this is the second substrate which is used, and basically what happens is that this undergoes condensation with this product uh, formate, and we will get this type of monovalinate as the product. And this monovalinate on deformulation, so here hydrolysis of this group will take place and hydroxyl group will be generated back, and then hydrogenation in presence of palladium and charcoal, that will hydrolyze this group and amino group will be generated back, and we will get valganciclovir as the product. So this is how ganciclovir can be converted into valganciclovir through this methodology. Then another method for the synthesis of valganciclovir is that if instead of triethyl orthoformate we use this precursor triphenyl methyl chloride. So when this is used, basically what will happen, this will react with one of the hydroxyl groups. This is a symmetrical hydroxyl group. Either this hydroxyl group or this hydroxyl group, we will get the same. So here this OH group, or because of the presence of two lone pair of electrons on this oxygen, will act as a nucleophile, and this will attack this carbon with elimination or substitution of this halogen, and this will get attached to this oxygen. So protection of one of the hydroxyl groups will take place through this triphenyl methyl chloride. Then this intermediate which is formed, that is N-no-bis-trityl protected compound, reacts with N-benzyloxycarbonyl L-valine, and condensation between these two will take place, and this condensation between hydroxyl group and this OH group, right? So basically a esterification is being done, and then we will get this type of product. Condensation will lead to formation of this type of ester linkage, and then in presence of hydrogen, uh, in presence of HCl water or trifluoroacetic acid. Basically, the protection at this oxygen, this nitrogen and this oxygen will be removed at both the places under acidic conditions. So that is either in presence of HCl water or in presence of trifluoroacetic acid. Both these protections they will be removed, and the hydroxyl group and amino group they will be generated back. And then on hydrogenation in presence of palladium and charcoal, hydrolysis of this uh, group will take place, and the deprotection of this amino will be generated, and we will get Belgian chloride as the product. So basically, if we see the method is similar to what we have seen in the previous one. Only difference was that instead of trimethoxy, trimethyl orthoformate, we have used triphenyl chloromethane or methyl chloride as the starting material. Then is Cidofovir. This is primidinone derivative which is used as the substrate, and this primidinone derivative when reacted with this epoxide, basically what will happen, this nitrogen and nitrogen will act as a nucleophile and will attack this carbon with the opening of the epoxide ring, and we will get this type of optically active alcohol as the product. Then this will react with this tosylate phosphate ester as the reactant, and basically uh, this will act as a nucleophile, attack this carbon with the removal of tosylate, and we will get this type of phosphate ester. And then in presence of HCl, protection of this oxygen will be removed and hydroxyl group will be generated back, and in presence of trimethyl bromide, hydrolysis of these phosphate ester will take place, and this will be converted into phosphoric acid derivative. And further on reaction with ammonium hydroxide, the protection of this nitrogen will also take place. Hydrolysis of this carbon nitrogen bond will take place, and amino group will be generated back, and we will get cidofovir as the antiviral agent as the product, which is a DNA polymerase inhibitor. These are the references which have been used for preparing this lecture. Thank you very much.